So the next thing we want to do is say we know that a capacitor, if it's charged, has energy in it. So the question is, how much energy is stored in there? And I'm going to use U for the electrical potential energy. So what's the electrical potential energy stored in a capacitor? Now, you naively might say that you've got here a capacitor here, okay, and we've got, a 12-volt battery, and we've got let's say this is going to be a 0.125 farad, so 1/8 of a farad capacitor. Now that's really a huge capacitor, but let's say that naively you might think that you remember that the electric potential is going to be the electrical energy per charge, and so you might think, oh, it's just going to be Q times V, and so that would be all we'd have to do is find Q up there. Okay, and so Q is pretty straightforward because we know that C equals Q over V. So Q is going to be C times V. Okay, and so that would be C times V times V. So that'll be CV squared. And so you would look at that and say, oh, wow, that's real simple. So that would be 0.125 times 12 squared, which would be 18 joules. Okay, that sounds simple, except it's wrong. Okay, so that's not really what happens. Okay, now the reason that's not what happens is, you remember when you're charging thing up, the first bit of charge goes in easy, the next one is harder, the next one is harder, the next one, so the first charges have less energy than the last charges. So that means this is not going to be that simple right there. So it's going to be considerably more complicated. Well, at least somewhat more complicated. And so we look at, so let's think about this. We're charging our capacitor. So the total energy is going to be adding up all the little differential bits of energy. So that's going to be basically integral of du. Okay, so all we got to do is find what is du. Okay, so we're kind of on the right track here in our original idea, in that we said that the u is the v is going to be the u over per charge. So u is going to be qv. So that would suggest that du is going to be v dq. Okay. What's v? Well, V is the voltage that's on the capacitor. So the voltage on the capacitor, okay, we know that capacitance is defined to be Q over V. So the voltage is going to be Q over C dQ. Okay, so voltage is Q over C, because the more charge you have here, the bigger the voltage. So if I put that all together, this is the integral from 0 to the final charge of Q over C dQ. Well, we know how to do integrals. Okay, so 1 over C comes out, so the integral 0 to Q of Q dQ. So that's going to be 1 over C times 1/2 Q squared. In other words, we would say that the energy stored in the capacitor is Q squared over 2C. Okay. Well, we know that the Q on the capacitor is also related to the voltage on the capacitor. Okay. So the Q on the capacitor is C times V, right? So Q squared is going to be C squared V squared. Okay, so that means that this could also be written as 1/2 CV squared. Okay, so that is going to be the charge that is on the capacitor. Back to our original problem in which we were connecting up this capacitor here. Okay, 12-volt battery, 0.125 farad capacitor. Well, the total energy stored once it's charged, because it takes a while to charge up, once it's fully charged, then the energy in the capacitor is going to be 1/2 CV squared. So that's going to be 1/2 times 0.125 farads times 12 volts squared. Okay, and so that turns out to be 9 joules. That's still an awful lot of energy. That's actually enough to kill you if that amount of energy is transferred across your heart. Okay, and so that's why capacitors can be somewhat dangerous to mess with if you're not real careful, particularly the big capacitors. In fact, that's really kind of what happens is if your heart is not working properly, in other words, if it's fibrillating, that means different parts of it are beating out of sync with each other, then what they do is the paramedics will come along and they will apply a defibrillator. And the way a defibrillator works is it has a bank of a whole bunch of capacitors. And it's really a whole bunch of capacitors in parallel is what they've got in there. And so you have a whole bunch of capacitors and you charge them up. It takes a little while to charge them up, so it charges up, and then what you do is connect that to the paddles on either side of the patient, and poof, the energy goes, in a fraction of a second across the patient. And so the idea is if your heart is fibrillating, this blast of energy going through there stops it. Okay. Fibrillating means different parts of the heart are instead of going thump, 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 it's like quivering here, and different parts are beating randomly. And so if you stop it all at once, then the hope is it starts back up, going thump, 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 like it's supposed to be going. Okay. Now that's why if the heart is not beating at all, defibrillator will not work because it's already stopped, and so the defibrillator does not start a heart that's in full arrest. Okay, what it does is it stops a heart that's fibrillating, and the hope is it actually starts back up in sinus rhythm or in something close to that, in some kind of like sustainable rhythm at any rate.